All right, guys, this video is going to correspond with homework 6-9, and we're going to start to introduce the exponential function and its graph. So far we have talked about laws of exponents, and we've talked a little bit about manipulating and solving equations involving exponents, but now we're going to get into actually looking at the graph of the exponential function. So the first thing that we're going to do is we're going to graph the first equation here, which is y equals 2 to the x. So to do that, we're going to go to y equals, and we're doing number 1 here, and we're going to press 2 to the x. All right, so remember you're using your exponent button for the x. So now we want to go back to Zoom 6, which is Zoom standard. And if you're having any trouble, just make sure when you go to y equals that your plot is off. If you see a highlighted plot, you want to hit enter to hit it off, and then Zoom 6, okay? So this is called exponential growth. As you can see, from left to right, it's starting very shallow, and then the slope is increasing and it's getting steeper as we look to the right. So we want to graph, specifically this one, we're going to graph on a restricted domain. If you look, it says from -2 to 2. So let's remind ourselves that this is called a restricted domain, and it's from x equals -2 to x equals 2. Okay, so these are the x values corresponding to the brackets there. So we're going to go to our table and we're going to type in, we're going to look at the y values that correspond to the x values from -2 to 2. So I'm going to scroll to -2, and I'm going to copy down the values I have here. I have 0.25, 0.5, 1, 2, 4, 8. Okay, so now we're going to go over and graph it. So when we graph it, remember we need to establish a scale. So you want to show the person that you're counting by ones along the x-axis and the y. If you choose to go by ones, make sure you put that in. And then we're going to label our, we're going to plot our points. So we have -2, comma, 0.25-ish, so 1/4. And we have -1, 1/2. 0, 1, which is called the y-intercept. Remember, the y-intercept is when x equals 0. And then we have 1, 2. This is 1, 2. And then we have 2, 4. And we could keep going with this if we wanted to. The next one was 3, 8. But they told us to go from -2 to 2, so we're going to stop. So now we're just going to connect the dots. And we are not going to put arrows on the graph because with a restricted domain, you have to just leave it like that with the endpoints with dots, okay? So the y-intercept was 1 or 0, 1 if you put the coordinates. All right, now let's look at 1.2 to the x. So this is also an exponential function because the x is an exponent. So we're going to change our base to 1.2 to the x. So we have to say, how are we going to predict that this is going to look different than 2 to the x? So if we hit graph, take a look at this and think about how it compares to y equals 2 to the x. All right, so first let's copy down our table from -2 to 2. Zero, 1 again, that's in common. 1, 1.2, and 2, 1.44, okay? And then we're going to sketch the graph, okay? Graph it, sorry, we're not sketching. If we sketched, it would be a little less formal here. So we have starting at -2, comma 0.6, so a little higher here, the -2, and then -1.83, 0, 1, same y-intercept, 1, 1.2, and 2, 1.44, okay? So I'm hoping if I asked you, what do you notice? And again, I'm not putting arrows on this graph, I'm just connecting the endpoints here with dots, and that's it. I'm hoping what you notice is that the second graph, which has the base, this is called the base of 1.2, is shallower than the base of number 1, which is 2. So number 1 is growing faster than number 2. This is shallower, and this is not growing as fast of a rate as this one. This is steeper. Okay, so it says make some observations. What do you notice? What do they have in common? What is different? So I'm hoping you also notice that one thing they have in common is the y-intercept. The y-intercept is 0, 1, or just 1. And look, they're both crossing here at 0, 1. And now if I asked you why, I'm hoping you realize that when you're on the y-axis, that's when x equals 0. And when x equals 0, if you look at the exponent, that means that if you plugged in the exponent of 0, what will you get every time? What's anything to the 0 power? I'm hoping you're going to say anything to the 0 power is 1. So that's why both of them have a y-intercept of 1, because when you plug in x equals 0, y will equal 1 regardless of the base. And then also note when the base is 1.2, it's shallower than the base of 2. Y equals 2 to the x is steeper growth than y equals 1.2. It has a greater rate of growth. All right, so now the next one is going to give us another restricted domain. It's another way of looking at that same domain that we just did. So look down here at the next one. And notice we could have written this the same as -2 to 2, like this, with those brackets, but this is just another way of looking at the same thing. So the next one we're going to graph is 1/2 to the x. So go to y equals, and just change your base to 1/2 to the x, okay? You don't need the parentheses, or you could put the parentheses, whatever. So now I'm hoping you're seeing a glaringly obvious difference here in that instead of this is growing from left to right, it's actually going down or decaying. We call this exponential decay. So let's copy down the table from -2 to 2. So we have 4, 2, 1, 1/2, and 1/4. 4.25. And I'm also hoping you're noticing that the y-intercept is the same, 0, 1. It's the same. Here it is. And I'm hoping you're understanding why now, because if you plug in x equals 0, you're going to get 0.5 to the 0 power, and anything to the 0 is 1. So you know this is going to be 0, 1. Okay? All right, so let's quickly graph the rest. So we have -2, 4. Then -1, 2, 0, 1, 1, 1/2, and then 2, 1/4. Okay, again, we're going to connect the dots, but we're not going to put arrows on the graph, so you see it's decay. All right, and the y-intercept is 0, 1. So I'm hoping you're noticing here, if you look above it at 2 to the x, that the points are in common with 1/2 to the x. They look pretty similar, don't they? -2, 4, 2, 4, 1, 2, -1, 2. Interesting. What transformation do you think is happening? Are you saying maybe it's a reflection over the y-axis? Interesting. Interesting. Anyway, let's keep going. 1/3 to the x. Here we go. 1/3 to the x. Go to y equals. Okay. Let's copy it down. All right, so we have -2, 9, 9, 3, 1, 1/3, and 1/9. Okay, so again, we want to establish a scale. Let's quickly graph this one. -2, 9. -1, 3. 0, 1. Oh, same y-intercept. 1, 1/3, and 1/9. Here it is. All right, so do you guys see with this one, 1/3 to the x is steeper than 1/2 to the x. Steeper slope, especially to start. It's really steeper. Interesting. Okay, so what do they have in common and what are they different? All right, so in this case, y equals 1/3 to the x is steeper than y equals 1/2 to the x. we're going to talk about it has to do with the base. The base is going to control the rate of growth or the rate of decay in this case. So this one is actually decaying at a steeper rate than the other one, the 1/2 to the x. And then a similarity is that they have the same y-intercept of 0, 1. Oop. So now I'm thinking, can we make a connection between 2 to the x and 1/2 to the x and 1.2 to the x and 1/3 to the x? Well, actually 1.2 is not really related, but let's just talk about 2 to the x and 1/2 to the x, okay? Y equals 2 to the x versus y equals 1/2 to the x. These two are reciprocal bases, 2 and 1/2. And it turns out 1/2, if you rewrote it as base 2, 1/2 is really 2 to the negative first power. So if you think about it, this is really 2 to the negative x. Thus, the negative is on the x, and when you negate the x, that's a reflection in the y-axis. So that is the relationship between 2 to the x and 1/2 to the x. This one is growth, and this one is decay, because it was actually that mirror image over the y-axis. So if I had gone back to my picture, y equals, and I had typed in 2 to the x and 1/2 to the x, you're going to see that they're a reflection of over the line y equals x. So let's sum this all up here. These graphs are all examples of what we call exponential functions because the x is in the exponent. Exponential functions. You should have seen them before, I think, in Algebra 1. And the basic equation for the general exponential is always in the format y equals ab to the x. And we're going to talk about more what that means in class, but that's the basic equation, okay? And these components are going to play a role in if the graph is growth or decay. So the basic characteristics that you need to know are the domain and range. So the domain are the x values. So if you look at my picture, the domain goes on forever left and right. So we call that domain, you could either say the words all real numbers, or we could say from negative infinity to positive infinity because it goes on forever left and right. The range is the y values, which is dictated by the down and up. So if you look down and up, the lowest y value is the x-axis, which is around 0. But there's actually an asymptote at 0. In fact, the graph is approaching but never touching that asymptote. So that is called a horizontal asymptote because it's going like the horizon, going across. So the equation of that asymptote is y equals 0. Or you guys could write the x-axis. It's approaching but never touching that asymptote. And then the range, the y values are from 0 and then all the way up to infinity. 0 to infinity, okay? And we're not including 0 because there's an asymptote there. So another way to write that is to write y is greater than 0, meaning that we're not including 0, but we're including everything above it. Now let's talk about end behavior. You guys remember we did this notation earlier in the year. As x approaches positive infinity, so as you're looking to the right, where is the graph headed? If it is growth, the graph, let's go with 2 to the x, the graph is going up to positive infinity. And as you look to the left, the graph is approaching the asymptote of 0. Now, if it were decay, it would actually be the opposite. So what I'm writing here is for growth. Okay. I'm just going to spotlight the decay function really quick. If it were decay, then as you look to the right, it would be approaching 0, which is the horizontal asymptote. And as you look to the left, it would be approaching positive infinity. Okay, now let's go back to growth again. We're going to do the increasing interval. So we talked about when the graph is increasing is when it has a positive slope. So it's actually going up the whole way if it's growth. So the interval is the entire thing, which is negative infinity to infinity if it's growth. And then the decreasing interval is never, because if it's growing, it's never decaying. If it were decay, it would be the opposite. So there would just be decreasing the whole way from negative infinity to infinity, and there would be no growth at all. All right, let's go back to 2 to the x again. Is it growth or decay? We're going to do 2 to the x here. So 2 to the x we said is growth. And what was the y-intercept? We said was 0, 1. Now, I know there's a lot of vocabulary. I know this is kind of long. It's kind of boring. I get it. That's why we made a video, so we don't have to hear me talk about it in class tomorrow. But basically, these are all vocabulary words that you've heard this year: domain, range, asymptotes, end behavior, increasing, decreasing. But now we're putting it together in the form of a new function. And so we can see the beauty of this new function and the asymptotes and everything involved with it. We're going to talk more now tomorrow and in class about the base and how the base plays a role in the graph if it grows or decays. And we'll also talk about the other coefficient, which is the a value, which we're talking about up here, y equals ab to the x. So I will see you tomorrow. Thanks for listening.